So section 8.2, using factoring to solve quadratic equations. So recall the following from the last section, our zero factor property. So if two quantities being multiplied together are equal to 0, then one of those two quantities at least one of those two quantities has to be 0. So the product of two quantities is 0, then at least one of the quantities is 0. So in the last section we learned how to factor certain types of quadratic expressions. And rewriting an expression like x squared plus 2x minus 15 as an equivalent factored expression, quantity x minus 3 times the quantity x plus 5, is called factoring an expression. And when you write an equation in this form, factored expression equals 0, we're going to see it's going to be easier to find the values that make the equation true because we're going to use this zero factory property. So this says to solve the following for x. So some number take away 3 equals 0. Okay, so we could either, by inspection, just kind of look at that and say, well, that has to be 3. 3 take away 3 is 0. Or if we really had to, we could think of adding 3 to both sides and getting x equals 3. Okay, well, here we need some number that when we add 5 to it, we get 0. So again, we could just think about what that number would have to be and say, well, the only thing that makes that true is x equals negative 5. Again, it is a linear equation, so we could solve by subtracting 5 from both sides. Either way, we get x is negative 5. But now let's think of these quadratic expressions that we've been looking at. Now I have x minus 3 times the quantity x plus 5 equals 0. Well, if we use the zero factor property, I'm thinking of two numbers and their product is 0, then at least one of these two numbers has to be 0. So either x minus 3 is equal to 0 or x plus 5 is equal to 0. And we just said this means x equals 3 or x is equal to negative 5. Okay. And so in this form, it's much easier to figure out what makes that equation true than it is to think about what numbers plugged in here make this equation true. But now we know what those numbers are. One of them is 3. So 3 squared is 9. 2 times 3 is 6. So 9 plus 6 is 15. Take away 15 is 0. Okay? And negative 5 is another one that makes, when this is set equal to 0, makes that equation true. So in the last section, working on factoring was giving us one of the steps that we needed in trying to solve these equations. So in this section, we're going to learn how to solve quadratic equations. So again, solve means to find values of variables that make the equation true. Okay, there may be more than one value that does that. We've had equations that have more than one variable, so that's why I've put the S here in parentheses, whether it's one value or values or variable or variables. So a quadratic equation in one variable. Okay, it's an equation that can be written in the following form. So we have our ax squared plus bx plus c equals 0, where again a cannot be 0. So given f of x equals x minus 2 times x minus 6, answer the following. So first we're asked to find the x-intercepts. Okay, so the x-intercepts are of the form an x-coordinate where the y-coordinate is 0. So again, if this point is on the graph, it has to make this equation true. So we're going to plug in 0 for y. The output here is 0 equals x minus 2 times x minus 6. And again, we've got product of two things equal to 0. So one of these factors has to be 0. So either x is 2, or if we add 6 to both sides, x is equal to 6. And if we're looking for our y-intercepts, we'll put these together as some ordered pairs here in a second. We're looking for the y-coordinate when x is 0. So this means we're going to plug in 0 for x and solve for y. So we're going to get y equals 0 minus 2, 0 minus 6. So we're going to get a negative 2 times a negative 6, so y equals 12. Okay. So now if we put the ordered pairs together here, that tells us our y-intercept is at the ordered pair 0, 12. And our x-intercepts, we have one at 2, 0, and another at 6, 0. So now we're asked to compute f of 4. So we want the output on the graph when the input is 4. So f of 4, again, we've got kind of parentheses within parentheses here, but we're going to write that as 4 minus 2 and 4 minus 6. So here we got 4 minus 2 is 2, and 4 minus 6 is negative 2, and 2 times negative 2 we get negative 4. So we have f of 4 equals negative 4. Okay, which again, if we put those together as an ordered pair, input of 4 gives us an output of negative 4, gives us another point on our graph. So we've got a point at 4, negative 4 is on the graph. Alright, so now we're asked to use the points from above along with the axis of symmetry to sketch the graph. Okay, so we've got our y-intercept, so on the y-axis it's going to intersect a little bit off the graph here, but up here at 12. And then we have an x-intercept at 2 and another one at 6. And then we have this point at 4, negative 4. Okay. So remember our point is, and it says to use the axis of symmetry. So midway between these 2 points has got to be our axis of symmetry. And that does pass through this point. And so the point that the axis of symmetry goes through must be, that is our vertex. And so we've got this point over here. So here's our axis of symmetry, and it's 4 units to the left. There would be another point over here at 4 units to the right. So we have this point at 0, 12. Okay. But we would also have this point over here at 8, 12. Okay. And we've got our point at 2, 0. And another one over here at 6, 0. Okay. And then this axis of symmetry, it's a vertical line. And so a vertical line has the equation x equals, all the x coordinates on this line have an x coordinate of 4. Okay, so here's some of our important pieces for that parabola as well. And then if we kind of play dot to dot, and put some arrowheads here because they do keep going in on both of those ends. So again, we've got our graph. So here we've got our x-intercepts, our y-intercept, our vertex, and our axis of symmetry.